Hello, everyone. It's good to be back again. And if you have been following us, we have been delivering a series of webinars covering a variety of topics around cloud, DevOps, containers, and IoT. And this time, I'm very excited to bring what is called as Apache Kafka. This is in continuation with the IoT webinar that we have done a couple of months ago. So this session is meant for absolute beginners who are looking at learning what is Apache Kafka and how to get started with it. So I have an interesting agenda lined up for you. We're going to get started with an overview of Apache Kafka, basically understanding when to use Apache Kafka and appreciating the whole platform called Apache Kafka. And then we'll take a closer look at the architecture, followed by a quick walkthrough of key concepts and terminology. I'd also show you how to set up Kafka effortlessly in your local dev environment. Whether you're running Windows or Mac or Linux, it's fairly easy for you to get started with Kafka and play with some of the concepts that I'm going to demonstrate. And finally, this session is all about Kafka in the cloud. So I'm going to show you how you can spin up your own droplet in DigitalOcean and install Kafka in the cloud. So let's get started. So enterprise messaging has been the biggest challenge for many in the recent past. If you have been noticing, there is a deluge of data coming from a variety of sources. Even before Internet of Things became popular, data was always getting generated, it was acquired, it was stored, processed, and analyzed. But of course, it is IoT that has made data more valuable. But let's step back a little and let's look at the challenges that enterprise messaging architects and developers faced before Kafka. So let's start with a hypothetical use case where you are running a cluster of web servers, and these web servers are generating a lot of logs. So these are front-end servers that are generating logs very frequently, and you need to look at them as they're getting generated. So you start collecting the metrics as well as logs generated by these servers. So metrics are basically the parameters related to the server health, as well as the application logs that are emitted by web servers like Apache or Nginx. So when you have just a couple of servers and you're gathering the metrics and gathering the logs, it is fairly easy. And once you actually configure this same setup and once you think everything is in place, you might actually see additional use cases and additional opportunities to optimize. So once we are done with the basic metric aggregation by setting up a dedicated server that is basically pulling the logs and pulling the metrics from the front-end servers, let's say you now want to expand it further to a set of servers that you're actually running. Assuming you're running a slightly complex e-commerce deployment, you have an elastic front end that is running multiple web servers. Then you have a database deployment in HA. That means you have a master, you have a slave. Then you have a chat server for real-time communication with your customers. There is a shopping cart server dedicated for handling shopping cart transactions, and then there is a backend payment gateway integration server. So once you have these many servers and your requirements are also increasing, you need to create a mesh topology which looks something like this. So you will end up creating multiple log aggregation or metric aggregation servers. Each of them are responsible for a specific operation. For example, one block that you see here is responsible for storing the metrics for long-term analysis. The other one is responsible for showing you a real-time dashboard on how your transactions are flowing and how the logs are being aggregated. You might want to set up another server which is basically responsible for monitoring the database performance and database transactions. So now when you actually have this kind of requirement, you will end up creating a very complicated setup just to manage the logs and metrics coming from your entire deployment. And as you see, the arrows are connected across servers and across multiple log aggregation units. So this is going to be very complicated. And as you start increasing your servers, and as you start increasing the demand for analyzing and processing logs, you might end up adding more layers at the top and at the bottom. So this is going to be very, very complex. Then you finally decide that you're not going to deal with so many log aggregation or metric aggregation servers, but instead you want to create a centralized log aggregator, which is going to first collect all the logs coming from multiple databases or multiple servers, and then it forwards it to a variety of metrics and log processing servers. And this actually seems to be an elegant solution, because now you are avoiding the mesh topology and you are now creating a centralized mechanism to collect all the metrics, all the logs, and then forward it to appropriate backend log processing servers. So this seems to be pretty elegant, clean, and a manageable way of dealing with logs. But then eventually you might also end up creating multiple store and forward servers, one for metrics, which is basically the server metrics like the CPU utilization, the memory utilization, and so on, one for exclusive logs, and one for clickstream and tracking your actual transactions. Now you're actually dealing with multiple such pub sub or store and forward servers, and again, this is not going to be easy. So interestingly, this is the typical use case and typical topology that most of us are going to deal with. You can actually replace the servers with IoT devices and or any other device capable of generating data. You are going to have exactly the same challenge. So where exactly Apache Kafka fits in, and how do we actually deal with it? So once you have Apache Kafka, you basically replace the multiple store and forward or pub sub servers with just one Apache Kafka installation or an Apache Kafka cluster. So this is going to be your central piece, the central architecture that is responsible for collecting the metrics, logs, click streams, and then feeding that to a variety of systems that know how to deal with these incoming data points. So the bottom line is Apache Kafka is basically the pub sub engine, which is very high throughput based and which is highly performant, highly available. And this is responsible for becoming the core, the cornerstone of your enterprise messaging architecture. It doesn't matter what kind of data is being pushed to Apache Kafka. As I mentioned, it can come from a variety of data sources, and it can be consumed by a variety of applications. But Kafka can become the intermediary layer managing the communication of these data points across the stream. So that is basically the responsibility of Apache Kafka. It is the central pub sub engine that is capable of ingesting data at high velocity and dealing with multiple consumers or multiple subscribers that are processing this data as it enters. So that's the high level overview of Kafka. But taking a closer look at it, as I mentioned, it is basically a pub sub messaging system. It's fundamentally different from other pub sub systems that you may be familiar with. For example, RabbitMQ or Microsoft Message Queue or WCF, Apache Cupid. All of them are queue-based message-oriented middleware, and they cannot really deal with the amount of data that Kafka is capable of dealing with. And that's one of the reasons why Kafka is becoming the de facto standard for ingesting high velocity, high throughput data. But at the heart of it, it is basically a pub sub messaging engine. It was developed at LinkedIn a few years ago because LinkedIn was dealing with a lot of data and it has to be fed to multiple systems, and they didn't know how to deal with it. So they created Kafka internally to solve their own problem. And eventually it got donated to Apache. And it is one of the top projects at Apache Foundation, and it's being used by a variety of companies. So think of Apache Kafka as a distributed commit log or a distributed streaming platform. So a commit log is basically a mechanism which is almost like a database log where anything that takes place in the system gets committed and it gets appended to the end. So Kafka basically functions like a commit log where every message is going to get appended to an existing file or an existing storage mechanism. And it is also a distributed streaming platform because multiple sources can start streaming the data concurrently, and Kafka can handle that and forward it to appropriate consumers. So one of the key areas that Kafka shines is the durability of data and the reliability of data. So what happens when the data enters Kafka, but the consumers who are responsible for processing it are offline, or they are currently unavailable due to a connectivity issue, or they have just crashed? So you can define what is called as a retention policy that can store data durably, and it can wait till one of the responsible consumers come up and start processing the data. So it is highly durable and reliable. Now, reliability comes in when the servers actually responsible for brokering or forwarding these messages crashes. So how do you handle that? So Kafka is actually not designed to be a single point of failure. In fact, production deployments of Kafka have multiple nodes, multiple servers that belong to the cluster. And even if one of the nodes or one of the servers in the cluster crashes or goes offline, it immediately transfers, or basically one of the other nodes kick in and become active, and they take over the entire mechanism. So there is no single point of failure when you have a Kafka cluster. So that is the reliability part of it. It can run on just a single node, a single server, or it can run on hundreds of servers very efficiently. So that is the architecture which makes Kafka extremely reliable. So data is durable because it can retain data till one of the consumers come up and start processing it. It is reliable because there is no single point of failure, and there's a cluster that is responsible for forwarding the messages and storing them without going down or without actually bringing down the entire cluster at the same time. There are over 2,000 firms that use Kafka in production, from Netflix to LinkedIn to a variety of companies that heavily depend on Kafka in production. And many Internet of Things platforms, IoT platforms, are also dependent on Kafka for ingesting high velocity data. So Kafka actually becomes very, very powerful in IoT use cases, because when the sensor data is going to be ingested to the platform for further processing, it's actually ingested to a Kafka endpoint. Many other managed cloud services that you may be familiar with, like AWS Kinesis or Azure Event Hub or IBM's Message Hub, all of them are modeled around Kafka. So it's a very popular ingestion service in the cloud, but it can also be deployed as containers or as VMs running on premises. So what are the use cases of Apache Kafka? First thing, it is basically a messaging broker. So anything that is exchanging messages, any system that is heavily dependent on sending messages back and forth can leverage Apache Kafka. Activity tracking, for example, in e-commerce portals and heavy traffic websites, the clickstream analysis can be done by sending the data to the processing systems via Kafka. So activity tracking is another popular use case. Of course, metric collection and aggregation. For example, as I mentioned earlier, if you want to gather the metrics from servers or application logs coming from your database, app servers, and web servers, all of them can go via Apache Kafka to their destination. Stream processing, this is extremely popular. In fact, Kafka has an extension called Kafka Streams that makes it easy to stream data for near real-time processing. So when combined with technologies like Apache Spark, Apache Storm, and Hadoop, Kafka can become the gateway to IoT data. So there are many popular deployments and very powerful architecture patterns that are dependent on Kafka. So we are going to look at some of them in the use cases as well as demos. And finally, this can become an enterprise message bus where the whole enterprise architecture can rely on Kafka for exchanging messages. So this can be the central piece for sending a lot of messages across multiple systems. So these are some of the top use cases of Kafka. So taking a closer look at the high-level architecture, essentially these are the building blocks of Kafka. So you have source systems. So source systems could be anywhere from IoT microcontrollers to sensors to application servers to bare metal servers. So anything that is generating data is going to be the source system. This is going to be grabbed by producers. So producers are basically the source for Apache Kafka. They are responsible for acquiring the data and then ingesting them into Kafka. Some of these sources are not capable of talking to Kafka directly. For example, if you're running a tiny IoT device that may not run an Apache Kafka client directly. So that's where you'll actually introduce a producer. So the producer is going to typically run in a gateway or in an edge location, and it's going to grab the data as it gets generated, and it forwards that to Kafka. So that is the producer, which is basically the source of data. And once the data enters Kafka, it eventually reaches the consumer, which is responsible for receiving the data and forwarding it to a target system, which could be a real-time analytics or a machine learning engine, or it could be Hadoop. It could be anything that knows how to deal with the data. So the consumer is basically at the receiving end of the pipeline, responsible for receiving the data and processing it further. You also see Zookeeper, which is a very important part of Kafka deployment, and Zookeeper is responsible for maintaining the overall health of an Apache Kafka deployment. Even if you are running just one server of Kafka installation, you still need Zookeeper, because Zookeeper is going to be like the coordinator responsible for maintaining the health of Kafka cluster and tracking which of the brokers that are going to be available, which of the brokers that are unavailable, unhealthy, and automatically managing the overall health of the cluster. So Zookeeper plays an important role in Kafka deployments. So that's the high-level architecture. One of the popular patterns that customers use with Apache Kafka is what is called as the Lambda architecture. So here you see high-level Lambda architecture, which is very prominent in IoT deployments. So if you have been following my webinars, in one of my IoT webinars, I gave an example of connected cars, and I want to recap that to explain the role of Kafka in managing the Lambda architecture and also providing the actual analytics for the whole solution. So imagine you have a set of connected cars that are already on the road. So they are basically sending a lot of data points every minute. So some of those data points include the current acceleration details, the current fuel level, and many other metrics related to the current state of the car. So apart from all the metrics that these connected cars are streaming, there are a few that are very, very important to track in real time. For example, the acceleration, the availability of engine oil, the temperature of the engine. These are some of the metrics that needs to be monitored in real time. And there is also an onboard computer in the car which is sending a lot of metrics which will tell the health of the connected car in real time. So that is one of the data points. The other data point is, of course, the availability fuel level and the acceleration at which the car is going. Now, obviously, one of the companies that is actually running these connected cars, think of it like an Uber, is now interested in two things. Number one, it is actually planning to find out which car is going to have an anomaly or a problem that requires immediate attention. So it needs to monitor some real-time metrics and real-time health of the car that's on the road. Over a period of time, they're also interested in finding which of the cars are the most energy efficient or fuel efficient, and what are the routes that they can actually use to optimize the overall fuel efficiency. Now, obviously, to arrive at fuel efficiency and route optimization, they need data that is collected over a period of time. So it's not going to happen in real time. Whereas the metrics that are related to the car's health they require immediate attention, and they need to be tracked in real time. So now imagine all the cars that are connected and capable of sending the metrics are the data producers, and all of them are ingesting the data to Apache Kafka. Now every data point emanating out of the car would eventually hit Apache Kafka, and then the data points are going to be segregated into near real-time monitoring, which is what is called as hot path analytics, and the long-term historical trends that need to be stored and analyzed will go into what is called as cold path analytics. Now, when it comes to hot path analytics, these data points that need immediate monitoring and attention will go via Apache Spark, Apache Storm, and they'll also go through a machine learning model that can predict if there is a problem with the car based on the current data points. And if there is a fault that is found in the car, it immediately flags off the driver, the service center, and so on. So that is near real time, which is called hot path analytics. The metrics like fuel consumption, the acceleration, the route, all of that is going to go through the cold path analytics and will go into a historical database, something like a HBase or a Cassandra or any other NoSQL database. And eventually an Apache Hadoop cluster will process the data to find out which car is the most fuel efficient. So as you notice, it is going to be Kafka, which is acting as the gateway for all the connected cars. And as the data enters, it takes one of the two routes. One is hot path analytics for near real time, and the other one is cold path analytics for batch processing. But without Kafka, achieving this architecture and this pattern is going to be extremely difficult and very challenging. So in real world IoT use cases, Kafka is used for processing data as it comes, and also for forwarding it to systems like Hadoop for batch processing. So that is a quick use case that I want to touch upon. Now, looking at the core concepts, let's spend some time understanding the core concepts of Apache Kafka. So there is a producer, and as I mentioned, the producer is responsible for acquiring the data and ingesting that into a Kafka system. So producers are typically written in high-level languages like Python, Node.js, or Scala, Java, any of those. So they are responsible for grabbing the data from a variety of sources and interacting and interfacing with a Kafka cluster. Then obviously at the other end of the pipeline, we have a consumer, which is again written in one of the high-level languages, and it is responsible for receiving the data that is sent via the Kafka. So remember, Kafka in itself is not a processing layer. Its job is to efficiently broker the data. So it is not going to touch the data as it goes through Kafka. Its job is to make sure that every piece of data that is sent by the producer reaches one of the designated consumers. So it is consumer's job to deal with the data further, whether it is forwarding it to a Spark cluster or to an Apache Storm or Apache Hadoop. That is a decision made by the consumer, but the consumer is going to be at the receiving end of the pipeline. Then there are messages. So messages are basically the chunks of data points that we are going to send and receive. If you are familiar with databases, think of each message as a row. So this is going to represent one tuple at a time. So it is basically one data point that is responsible for one atomic unit or one atomic transaction. So as the data gets fed, it is going to be treated at one message at a time. So this is almost equivalent to the record in the analogy of databases. Then there are topics. Topics are basically the hubs, the central hubs responsible for collecting and forwarding all the messages, and topics are the contract between producers and consumers. So producers will precisely know which topic they're going to send the messages to, and consumers also know that they have to subscribe to this topic to receive the messages. So if messages are like rows of database, topics are like tables. So they are responsible for collecting and storing the messages based on the retention policy. So they are almost like the containers for messages, and in the database analogy, think of it more like a table. Then there is a very complex topic called partition, and partitions are created primarily to bring the scale. So again, going back to the database analogy, if you are familiar with sharding, think of partition as database shards. So when messages flow back and forth, they are going to be stored in one of the available partitions, and partitions are spread across available servers of Apache Kafka, actually called brokers, which I'm going to explain in a minute. And these partitions will bring in durability, availability, and high throughput. So they are basically like the shards. So every message that is sent by the producer is going to land in one of the partitions, and the consumer is going to basically pick the messages from one of the existing partitions. And partitions bring in a level of reliability, scalability, and durability to messages. More on that later. Then there are offsets. So an offset is more like a bookmark for the consumer. So what happens if there are 10 messages in a topic, and there is a consumer that has processed up to 5 messages, the 5th message, and then it has crashed. So Kafka is going to track how many messages were retrieved by the consumer, and it is going to make a bookmark. So next time when the consumer comes back online, it's going to pick up from where exactly it left. And how does it know what it did last time? Because it can query the offset and pick up the thread exactly from there. So an offset is more like a bookmark that's going to help consumers track how many messages are processed in a specific topic. You can override this by going all the way to the beginning and start processing all the messages. But offsets are a very important aspect of processing messages in a very reliable form. Then there are consumer groups. So consumer groups is a very interesting concept. So imagine there are messages that are coming into a specific topic, and you want to have 2 different consumers. One consumer is responsible for storing the metrics in a raw form. The other set of consumers are responsible for forwarding it to another processing system. And you want to make sure that both these set of consumers receive all the messages. So you create 2 consumer groups. For example, one for hot path analytics that can pull the messages and start processing in real time. Then another set of consumers which are responsible for feeding the messages to a Hadoop cluster, and that is a cold path analytics pipeline. So now you're actually going to create 2 consumer groups, and these consumer groups are subscribed to the same topic, and every message that comes in is going to land into both the consumer groups. But within a consumer group, there are going to be multiple consumers which will receive the message, and there is absolutely no overlap between the consumers. So basically, consumer group is like a collection of consumers that are guaranteed to receive the messages, and they are grouped to perform a common task. Going back to my analogy and my scenario, think of creating one consumer group for hot path analytics and one consumer group for cold path analytics. And the same data that enters Kafka will end up going into one of the consumer groups. And within a consumer group, there are multiple consumers, and there is no overlap between these consumers. So they are basically assigned to one of the partitions. More on this later, but you get an idea of a consumer group. It is basically to make sure that the same data is going to multiple destinations for different processing capabilities. And then there are brokers. So every instance of Kafka is called a broker, and broker need not translate to a physical server. Think of it more like a logical unit of deployment in Kafka. So when you end up installing Kafka, you actually end up creating a broker. You can have one broker per server, or you can have multiple brokers in the same server. Essentially, a broker is nothing but a JVM listening on a different port. So if you change the port on which the Kafka service is listening, you can launch multiple brokers on the same machine. And these brokers are coordinated by Zookeeper to make sure that they are healthy and they are evenly balanced in terms of their processing power. And finally, a set of brokers is called as a cluster. And again, the cluster is typically assigned or associated with a physical set of servers. But as I mentioned, a broker need not be a physical server. It is a logical instance of Kafka, and you can run multiple such logical instances per physical server or a VM, or you can split them for better scalability and throughput across multiple servers. So you can run one broker per server. And cluster is a collection of brokers, whether they are logical or physical. You treat multiple brokers as one cluster. So that's the quick recap of the core concepts. We have looked at some of these earlier, like producer and consumer, and I want you to pay more attention to partitions and consumer groups, which I'm going to demonstrate in the upcoming demo. So this is how we visualize topics and partitions. So as I mentioned earlier, partitions bring in additional scale to Kafka. So what happens with partitions is that you can take the same topic and you can spread that across multiple brokers. For example, when you deploy Kafka in a multi-broker environment, it is absolutely possible to run one partition of the topic in a different broker, and you can spread these partitions across multiple brokers. So this is going to bring in scalability. And when producers write messages, when they actually commit messages, they don't care about partitions. They just send the data to Kafka, and Kafka will decide which partition is going to actually get the message submitted by one of the producers. How does it decide? It basically tries to group multiple messages that belong to the same logical key, which is responsible for identifying the messages. So basically, let me step back a little here. So basically, when you are submitting messages to Kafka, you're actually dealing with a byte array, which has a key assigned to it. So it's a key value pair where both the key and value are essentially byte arrays. So when you send a message along with a key to Kafka, Kafka will hash the key and will put the message in one of the partitions. Next time when another message comes and when it has the same hash, it is going to assign that to the same partition. So based on the key that the producer is using, it is going to be assigned to one of the partitions. And when the consumer is going to read, it is going to be hooked to one of the partitions, and you will have those many consumers as the number of partitions that are directly processing the messages. And since partitions are very unique, for example, a message cannot be written to two partitions at the same time, it is guaranteed that one of the consumers will receive the message, and there is no duplication. So this will become very clear when I show you the demo. But for now, understand that partitions are like database shards that are spread across multiple brokers in a Kafka deployment. And based on the key of the producer, of the message submitted by the producer, they are going to be assigned to one of the partitions. How exactly are the brokers responsible for storing the topics via partition? So this is actually an illustration of how this is done. So let's say we have three brokers and we have two topics. So when we created the topic, we mentioned the number of partitions. So when we actually say that create a topic called topic 1 with 3 partitions, it is going to be creating each partition in one of the available brokers. And when we create another topic called topic 2 with just 2 partition, it chooses broker 1 and broker 3. You notice that there is no topic in broker 2 because we just need to create 2 partitions, and it has randomly picked one of the brokers to actually create the other partition. So that is the relationship between brokers, topics, and partitions. So topics are like the hubs responsible for managing homogeneous messages. All the messages that belong to a similar group will hit the topic, and each topic is further divided into partitions for better scalability and durability, and these partitions can be split across multiple brokers. So that's the whole concept of dealing with brokers, topics, and partitions. Consumer group, as I mentioned earlier, is basically the idea of creating a set of consumers that are processing messages from the same topic, but they get assigned to a unique partition. So now we have 4 partitions here, and we have 3 consumers. So when we actually launch this, you notice that consumer 0 is assigned to partition 0, and consumer 2 is assigned to partition 3, but consumer 1 is capable of reading from both the partitions because this cannot go idle. So when there is an uneven match of consumers with the available partitions, Kafka will automatically balance the available partition with consumers. So in this case, consumer 1 is going to read from partition 1 and partition 2, while the remaining consumers are dedicated to each of the partitions that are available. So now this consumer group could be responsible for processing all the messages, and we could create another and assign them to the same topic, and they are completely independent of the existing consumer group. So that's the idea of sending messages to multiple consumer groups, where each consumer is guaranteed to receive a unique message. So I covered a lot of ground. This has been pretty intense discussion around brokers and topics and partitions. So let's actually take a walkthrough of this, and it's going to be very clear on how we are going to deal with this. So it's time for me to walk you through a demo to put things in perspective. So how do we get started with Kafka? Fortunately, it is not very difficult. So there is a company called Landoop, and I want to show you the landing page of this company. So what they have actually done is they created a set of Docker containers for dealing with Apache Kafka. So I strongly encourage you to use Landoop's fast data dev Docker image to get started with Kafka on your local machines. And this runs anywhere Docker runs. That means you can safely run this on Windows, Linux, and Mac. And it also comes with a nice set of dashboards and visualization tools, which will make it easy for you to understand the core concepts when you're dealing with Kafka the first time. So I'm going to use the Landoop Docker setup to start with, and then we'll also take a look at setting up Kafka on DigitalOcean by spinning up a droplet. So let's switch to the demo. So the very first step is to launch the Kafka server as a Docker container. So as you notice, this is the Docker run command with an image called Landoop fast data dev, and it comes with a bunch of ports that we're going to expose, and all these ports are very essential. Some of them belong to Zookeeper, some of them belong to Kafka itself. So let's go ahead and run this Docker image. Okay, so this is now starting Kafka. To save time, I have already pulled the image. So what you actually see on the screen is launching Kafka. So it is already in the running mode. So now we have the broker, which is just one instance of Kafka that has started. So now we can actually go ahead and start publishing messages to it. So now I'm going to launch another terminal window. and I need some client tools to basically deal with the Kafka endpoint and the Kafka broker. So what I'm going to do now is use the same fast data dev image, but instead of running it like a daemon or as a background process, I'm going to get into the interactive terminal and I'm going to run the bash shell within the Docker container. So this will give us access to the tools that we need to deal with when we are talking to Kafka. So now we are inside the container, and now we have access to a variety of tools that we can start using. The other thing that I want to show you is Landoop comes with a fantastic set of dashboards. So the moment you start running the Docker container, you can fire up your browser and hit localhost 3030, and this is going to show you everything related to the local installation. So you can browse all the topics, you can look at how many brokers you have, how many connectors, and everything that is basically running within the deployment. So one of the interesting things here, I don't want to zoom in further, but you actually notice that these are the ports that are exposed by the container. So Kafka broker, schema registry, REST proxy, Zookeeper, and the web server, which is responsible for hosting this dashboard. So this is a great start in terms of learning Kafka and the core components that run inside the Kafka deployment. All right, so let's leave this and come back to the command line. So let's go ahead and use some command line tools. So the first one that I'm going to run is called Kafka topics. So when you type Kafka and hit enter, you'll actually notice that this container has a set of CLI or the command line interface tools, from producers to consumer to topics. You can do a lot of stuff just from the command line. So the very first command that I have run is to grab all the topics and list them. So before you can actually use, you should point the command line tool to the Zookeeper installation. So I have given Zookeeper followed by localhost 2181 port. That's where the Zookeeper service is listening. And this command basically lists all the topics. So these are all system topics. We haven't created one yet. You can also go back to the browser and look at the topics UI, and it shows some of the topics. So if you select the system topics, there are 5 topics which are shown even here. So we don't have our custom topics yet. So let's go ahead and create one. So the first one that I'm going to create is actually the topic called demo. So what I'm going to do now is point the CLI to the Zookeeper and then create a new topic called demo with just one partition. And there's also a concept of replication factor. So replication factor is when you have multiple brokers, you can actually define how many brokers are going to run the replica of this topic. Since we only have one, I'm going to keep this as replication factor 1. So every Kafka client, whether it is the command line or the SDK or the REST that you're going to deal with, you will need to either point it to the installation of Zookeeper or one of the Bootstrap servers. Bootstrap server is the broker responsible for the primary interaction. So we'll also deal with the Bootstrap server as we go through the demo, but for now we're actually pointing the Kafka topics CLI to Zookeeper. So let's go ahead and create our first topic called demo. So this is going to now create a new topic, and let's come back to the browser, refresh it to verify the creation of our topic. So there we go. Now we have a topic that we have created from the command line. The dashboard doesn't let you create, delete, or manipulate existing topics. It is only a view for you to access the messages. So you can't really create a topic from the browser. You still need the command line to deal with. All right, so now let's go ahead and list the topics again. So when we actually do this, it comes back and shows demo as one of the topics that we created in the previous step. And with that in place, let's actually start a producer. So now I'm going to run the producer. Okay, so okay, it is not taking the continuation. So let me run this again. So now we're going to run the producer, which is responsible for sending the data. And this is interactive. It is called Kafka console producer because we can interactively type in the data. So let's leave this as it is and create another terminal window and access the CLI all over again. Okay, so now we have the producer here, and let's launch a consumer. So now we are going to launch a consumer, and we are pointing it to the same Bootstrap server, and we are subscribing to the topic called demo that we just created in the previous step. So now let's actually launch the consumer. So this is the consumer and this is the producer. Everything is from the command line. All right, so let's leave this running here. Now I'm going to type some messages, and every message that I type here will show up in the consumer window because both of them are connected to the same Kafka broker. So this is one more message, and when I hit enter, it actually shows up here. And this is the most simple pub sub mechanism within Kafka. So we have one producer, one consumer, all of them running the command line level, and we have the broker right here. So very, very simple, and it doesn't use any partitions. It doesn't use any specific features that we have discussed earlier. This is the plain vanilla pub sub model. So now let's kill the consumer, and I'll continue typing yet another message from producer. Okay, and I'll add in another. So now what happens is when I launch the consumer, we are going to see only the new messages. Okay, so not even the new messages, whatever I'm going to type, this is the latest message and this shows up. Okay, the reason is we haven't added a switch to the command line to actually pick up the previously added messages. So let's actually go ahead and do that. So the next command that I'm going to introduce is accessing the messages from beginning. So now we are actually adding a new switch called from beginning. So now when I actually run this, it's going to pull all the messages that we have typed so far. And this is how you basically override the offset and go back to the beginning and fetch all the messages from there. So this is the most simplistic way of using Kafka, all from command line. We haven't even started coding, but I'm going to show you how to achieve the same thing with Node.js by using a custom library. But let's actually move to a slightly advanced scenario. And I'm going to show you a slightly complex use case, but it is more real world. So what I'm going to do now is actually walk you through a use case. Let's say we have a building, and every room of that building has a sensor, and all these sensors representing each room are streaming data about the temperature. So the temperature data from all the rooms that belong to a building are being streamed to Kafka. And now what we're going to do is create a consumer group that's going to pull these messages from each of the rooms. And as you notice, it's going to be like one consumer of the consumer group is going to end up getting the messages. So let's actually go ahead and execute this. So I'm going to run, I'm going to first create the topic. So, but even before that, okay. So first I'm going to create a topic called building 1, and it is coming with 3 partitions. replication factor is 1. That's because we are running just one specific broker. So the new topic is created called building 1. Okay. Now, what I'm going to do is start a producer, but pass these parameters that say property.key.separator is a comma. So what it means is when we actually launch this producer, we not only send the message, but we can also include a key. And key is obviously going to be the room, the number of the room that is responsible for the temperature. So now let's switch to this, and let me launch the Docker container in all the 3 windows. We need them here. Okay, so now the scenario that I'm trying to emulate here is we have one producer and 3 consumers that are going to be representing the same consumer group. So as I publish messages, you'll notice that only one of the consumer of the group will receive the messages. So now it's time for me to start the producer. So I'm going to grab this and run it here. So now we have the producer running. We haven't entered any message yet. And then I'm going to launch the consumer. So when I'm launching the consumer, you will notice that I'm explicitly mentioning the partition number. So I want to pull messages from partition 0. And it belongs to a consumer property group called rooms. So that means we're actually creating a consumer group to which this consumer belongs to. So now I'm going to run this in one of the consumer windows here. Okay, and we are going to launch another consumer as a part of the same consumer group called rooms. And this time it is assigned to partition 1. Okay, so it goes here. And then finally, we are going to launch the third consumer, which is assigned to partition 2. And all of them belong to the same consumer group, right? So now we have 3 consumers and 1 producer. So let me go ahead and type room 1 34.5. When I hit enter, you'll actually notice that the first consumer assigned to partition 0 received this. Now I'm going to enter, let's say this is a large building and I have 100 rooms. So from room 100, we are getting another data point, 28.3. Okay, and now we actually notice that the third consumer has received this. Okay, now I take a number which is in between, so room number 50, and there is no AC working there. It is pretty hot, so 39.1. Okay, it is assigned to partition 0. Okay, we cannot really expect or anticipate that it is going to land up on partition 1 because it is completely based on the key hash, and this is currently assigned to partition 0. So let's enter one more room, let's say room number 110 and 34.2. So now this has gone to the other partition. Now if I enter room 1 followed by a new temperature data point, it will obviously go back to the first one because it is already assigned. This specific key of the message is already assigned to partition 0. Now when I enter room followed by a value, it again goes back to exactly this. So the key takeaway from this demo is when a message is submitted to Kafka through a producer, it's going to take the key of the message, do a hash of that, to the same partition. Now, this will make it possible for you to process all the messages as they are coming across multiple clients, multiple consumers. So this is going to be very useful when you are processing data in real time at a very high velocity and high throughput. Now, let's take a look at the dashboard. And when I actually click on building one and look at the data here, now this is the simple view key value data. When you click on table, it actually shows you that room 1 is assigned to partition 0 and room 100 is assigned to partition 2. Any further message that comes up with the key room 100 will automatically go into partition 2. So this is the concept that I was trying to drive across, where depending on the key, it is going to be assigned to a partition, and only one consumer of the consumer group will get assigned to the partition. What happens if you have lesser number of consumers than the available partitions? Then obviously one consumer of the group will be assigned to more than one partition, and it will make up for that. But no message will ever sit idle without reaching one of the consumer. It might happen that if you launch multiple consumers, more than the available partitions, one of the consumer or more than one consumer might be idle because they may never get assigned to a partition because there are more number of consumers than the available partitions. So that is the idea of partitions and consumer groups followed by consumer. So this demo basically explains what I was trying to explain through the theoretical conceptual slide. So in the interest of time, let me take you back to the slide deck and talk to you about installing Apache Kafka in the cloud. So what we have seen earlier was a very simple dev environment where we ran Kafka and Zookeeper inside a Docker container. But if you are looking at production environments, it is recommended that you basically launch a droplet in DigitalOcean and then configure the server with some additional steps. To keep that simple, I have a link here. In fact, I would strongly recommend you to visit this. DigitalOcean has published a fantastic tutorial on installing Apache Kafka on Ubuntu 14.04. This was in August 2015, but it is extremely relevant. So you have all the steps that you need to follow to set up the Kafka installation. So at a high level, the steps are launch and configure the server, and then install Java, install Zookeeper, and then install and configure Apache Kafka. So I've also compiled the steps. For example, you need to configure the swap memory on the Linux box, because without swap, JVM might actually have a lot of issues. So you start by creating a swap file, and then you go ahead and create a Kafka user. And this is going to be the user context under which Kafka will run. And then you install Java with a couple of commands and make sure Java is up and running. And then you have the Zookeeper installation, which is pretty straightforward with just one command. Actually, let me launch a command window, SSH into the DigitalOcean droplet that I launched and show you some of these concepts. So, okay. So I already have swap memory. So when I actually type free-m, it shows that I have a swap memory that is already pre-configured. And then I have created the user called Kafka. I've already installed Java. So Java version is 1.7. That is good enough for Kafka. And then I have Zookeeper running. So when I actually type, "Are you okay?" Zookeeper comes back with "I am okay" response. And that's an indication that Zookeeper is healthy. It's up and running. And then I have gone ahead and installed Kafka. So for this, you need to basically run multiple steps. So you have to get the latest binary of Kafka, then unzip it, and then run it on the local machine. So the Kafka log will tell you whether the installation is successful or not. So obviously there are no errors, so everything seems to be fine. And finally, how do you test the installation? You again run the same Kafka console producer. So I'm going to run hello world on this, and it has successfully submitted. Now I can run the consumer, and it's going to show a couple of hello world messages because I have already published a few in the morning. So that's an indication that we have a perfectly configured Kafka installation in the cloud. And I promised you that I'm going to show you code to actually talk to the Kafka. Here I have very basic Node.js code. So here you actually notice that I'm using a custom NPM module called Node RD Kafka. It's a very popular one among the Node.js community. So I installed that with NPM installed, and then this is my producer where I'm actually publishing the data for building 1. Topic is building 1, key is room 1, and this is the temperature. And this is the consumer. So here we are basically subscribing to building 1 topic, and when the message arrives, we basically print it on the console. So pretty straightforward. So let's go ahead and execute these steps. Okay, so I'm going to have both the consumer and the publisher running here. So I'm going to run node producer.js. So it is running, and I launch node consumer.js. And as soon as this comes up, let me launch this again. Okay, so it shows up. So when the producer is launched, it prints 28.1. So let's try this one more time. Right. So this is basically performing the same pub sub, but from code. So one thing that I want to show you is if I grab the IP address of my Kafka droplet, come back to my code, and just replace the local host with the IP address, right? And run this sample again. So let me start the consumer first, and then let me launch the producer again. So to make it more obvious, I'm going to change the value. So let's make this 35. Okay. And I'm going to launch my producer again. So when I actually do this, you notice that the consumer is receiving. This time we are routing this from the cloud, because I have changed the IP address of the broker from localhost to the droplet floating IP. So now it's actually routing the message from cloud. So that's the beauty. You can write the code and you can keep switching between multiple Kafka brokers. So that brings us to the end of this session. This was Kafka for an absolute beginner. My overall objective was to introduce you to the core concepts and explain you the use cases of Kafka. So I hope you found that useful.